Hi all, this is Sai Jain Devireddy and today we are going to discuss paper A Metric Suit for Object-Oriented Design by Shyam R. Chidambar and Chris F. Kumar. Chris F. Kumar is a professor of information system at CAD Graduate School of Business at University of Pittsburgh and he has an H index of 48. Shyam R. Chidambar is an adjunct professor at Department of Management, American University, and now currently he is a CEO of Zigbee Q Services. This paper is published in IEEE in year 1994 and has 8,433 citations. The main agenda of this paper is to propose metrics which can measure unique aspects of object-oriented approach and evaluate these metrics against established criteria for validity. Along with this, the authors also intend to present empirical data from different commercial projects to show how these metrics may be used on real applications. With the shortcomings of the current metrics, many authors suggested a new set of metrics to evaluate object-oriented design. Many of these metrics lack theoretical knowledge or a theoretical base, which suggests that the new metrics are to be designed with a deeper knowledge of both theoretical and mathematical definitions. These metrics should be designed to measure unique aspects of object-oriented approach. Design of class is the most important part of object-oriented architecture. Object-oriented design as presented by Booch has 4 steps. First, we identify classes and objects from the requirements. Second, we establish meaning of each class and objects identified in the previous step, that is, each class is given a specific role to carry. Next, we look for any kind of relationships between classes, that may be inheritance. Finally, these classes are implemented with the methods which define the functionality of each class. While evaluating the metrics, we look for the following properties which are defined at the class level and see which property satisfies which metric. Non-corrosiness implies that each class should have a unique metric value, and non-uniqueness is a complete opposite of non-corrosiness. That is, two different classes can have same value for a metric. That implies both the classes are equally complex. Property 3 ensures that the design details are never missed in calculating a metric value. Monotonicity implies the value for the combination of classes should always have a higher value when compared with either class individual metric value. For example, if we take two classes P and Q, the combination of P and Q or P plus Q metric value should always be higher when compared with the metric value of class P or metric value of class Q. Non-equivalence of interaction. This implies that the metric value of class P and class Q are equal, but that doesn't mean the metric value of class P plus R should be equal to metric value of class Q plus R. Interaction increases complexity. This means that when both the classes are combined or interacted with each other, the metric value for the combination of classes should always be a higher value when we add the metric value of the individual classes. We've made assumptions for the distribution of methods and variables when we talk about each metric property. The assumption 1 is about the value of the elements xi, yi, zi, and ci. These values should be a random variable, and these are all independent and identically distributed, which means the value of number of methods, variables, and couplings are unique to each system. Coming to the assumption 2, two classes can have a method with similar functionality, but when we combine these two classes, the method from any one of the class will become redundant. And coming to assumption 3 is all about inheritance, which implies that System will have classes that depend on other classes. To evaluate these metrics, we need to collect data from the existing projects. For this, the authors have collected data from two different companies, which they have named Site A and Site B. From Site A, they have collected metrics data from 634 classes from two C++ libraries, in which they are used in a graphical user interface. But from Site B, they have chosen a different programming language, that is Smalltalk programming language, which is used for developing machine control and manufacturing systems. These metrics were collected from 1459 classes, and these are all of Smalltalk programming language. So with the data collected from the two different companies and from the different classes, the authors came up with these 6 new metrics. Let us see what these metrics define. So the first one is being the weighted methods per class. This means this is the sum of all the complexities of all the methods declared in a class. This can be used to indicate the development and the maintenance efforts for the class. The second one, the depth of inheritance tree. This indicates the maximum length of a path from a class to a root class in a system. It measures that how many superclasses can affect a class. The third one, number of children. Number of children indicates how many subclasses are going to inherit the methods of the parent classes. Coupling between object class. It is the measure of number of classes with which a specific class interacts by accessing them through variables or methods. Response for a class. How many methods are called or executed in response to a message received by the object of a class method. And finally, lack of cohesion in methods. It is the difference between the number of method pairs not having instance variables in common and number of method pairs having common instance variable. Now let us look at the individual results of each metric. Now let us discuss the results of DIT. And before that, let us see the viewpoints. The viewpoints of DIT suggest that if a class is deeper in hierarchy, then it will have more methods inherited, which makes the class more complicated and difficult for testing. Along with this, the design also gets complicated. With the deeper classes, there is a higher chance for reusing of the code. But by looking at the data, we can see that the site A has a DIT metric value of maximum of 8 and a minimum of 0, with median being 1. And for site B, maximum of 10, a minimum of 0 and median being 3. By looking at the median values, we can see that it has very low values, and by this we can interpret that the application is very close to the root. And by using DIT, we can see or we can suggest whether the code is top heavy or bottom heavy. Now, with the median values from site A and site B being very low, this means that it is a top heavy libraries. That means the designers of the code or the architectures, they haven't really used or taken the advantage of reusing the methods through inheritance. This means that there is a poor reuse of methods. So we can look at the metrics and evaluate that with the set of properties we see most of them possess a number of properties which we have seen in evaluation criteria. This also suggests that object-oriented approach is different in design features from more traditional approaches. These metrics also give insights to senior designers and managers who have no idea about the design of the system. Here is the reference of my paper. Thank you.